So hello guys, my name is Akash and you are watching Mathsopedia Academy by Akash. So today we are going to solve some important question related to your uniform convergence topic, which may NTA ask you in your CSI NET exam of 2026 of July. So here are question number 1. What is question number 1? We have to test the uniform convergence. Test the uniform convergence. The sequence, given the sequence Fn where Fn of x is equals to nx upon 1 plus n square x square for all x belongs to R. So in this question we have to test the uniform convergence. Fine. So solution. First we have to check it's pointwise convergent or not. So checking pointwise convergent. So here limit n tends to infinity fn of x is equals to limit n tends to infinity. If we took n both common from up numerator and denominator, then we get n square upon 1 by n square plus x square. And if we cancel out this one and take n tends to infinity, then this whole term will goes to 0. This implies this is equals to 0, which is your fx. So by the definition of pointwise convergent, for every x belongs to R, limit n tends to infinity fn x is convergent to fx. This implies fn is pointwise convergent to f. Pointwise. Now we are going to show it is uniform convergence or not. Uniform convergence. For that we must know the definition of uniform convergence, which I taught you in my previous lecture, which was in this playlist only. So you can tally that and get your knowledge from that. Fine. So in uniform convergence we have to see by definition fn x minus f of x must be less than epsilon for all n greater than equals to n, where n is your integer. So here in your question fn x is given x, nx upon 1 plus n square x square, and your fx is your pointwise convergent, which is comes to be your 0. So we have to put here 0 is less than epsilon for all n greater than equals to n. So if we take mod out, you get nx upon 1 plus n square x square is less than epsilon. Now we have to choose something, because initially we took fn is f uniformly. This means we took fn converges to f uniformly. So this definition can be applied. Fine. So for epsilon equals to 1 by 3, which is your equals to 0.3 something. Fine. And n equals to m, an integer, and your x equals to 1 by m belongs to R. So if we put all your things in your upper equation, epsilon and x, then we get what we get, m upon 1 by m, because n is your m, x is your 1 by m, upon 1 plus n square 1 by m square, this is your m square. When you cancel out, you get 1 upon 1 plus 1, which is your 1 by 2, which is less than 1 by 3. But this is not true, because 1 by 2 is 0.5 and 1 by s is 0.3, and this is not satisfied. Hence we got contradiction. So when we got contradiction, this implies Fn does not converges to F uniformly. Fine. Now coming to the second question, question number 2, we have to show that the sequence Fn where Fn is your x raised to power n is uniformly convergent on 0 comma k, where k is always less than 1, and only pointwise convergent on 0 comma 1. Fine, this is your question. So what this question asks? This question asks us, we have to show the sequence Fn where Fn is your x raised to power n is uniformly convergent. Where it is uniformly convergent? In the interval 0 comma k, where k is less than 1, and pointwise convergent on 0 comma 1. This means at k equals to 1. So first we have to check its pointwise convergent. Here is your function Fnx. Solution. Now what is your Fx? Fx, according to pointwise definition, limit n tends to infinity, f of n of x is your equals to 0 when 0 x 1, when x is your 0 then is 0 raised to power n, and when is your x belongs to 0 to 1 then is 0 point something raised to power n, and in both, when limit n tends to infinity, then this all values goes to 0. So n tends to infinity, this value is 0, and at x equals to 1 only condition, then this is your equals to 1 raised to power n. This means it is equals to 1. Thus the sequence converges pointwise to a discontinuous function. Sequence convergence to fx, where this fx is our discontinuous function on 0 comma 1. So our first condition is satisfied, that this Fnx is pointwise convergent only on 0 comma 1. Now we have to check its uniform convergent on 0 comma k. Uniform convergent. So we have to take definition. Fnx minus f of x must be your less than epsilon for all n greater than equals to n, where n is your integer. Fine. So what is your Fnx? Your Fnx is x raised to power n. So put it here, xn minus what is your fx? Your fs is 0 for x belongs to 0 to k. Fine, where k is not equals to 1. So this is your less than epsilon, where x belongs to close interval 0 to 1. Fine. Now, if, as we know that this implies x raised to power n must be less than epsilon, if we took cross multiplication like this, then this is equals to 1 by xn must be greater than 1 by n epsilon. Fine. Then if we took log both sides, log 1 by x raised to power n is greater than log 1 by epsilon, here is equals to n, because the property of log says that n will comes forward, so n log 1 by x must be greater than log 1 by epsilon. Putting n one side and taking all other things to the one side, and log 1 by e upon log 1 by x. As we see, if you move from 0 to 1, here x moves toward this, then this value is going to be your maximum, that is log 1 by epsilon upon log 1 by x increases with x. So its maximum, here is your k, maximum value being log 1 upon epsilon upon log 1 upon k, because x is belongs to 0 comma k. So here is your k is your maximum value, so when you put that, this value is increasing with x, so this value is your maximum. Fine. For k greater than equals to not equals to greater than 0. Fine. Now let n be an integer. This is your important step. Greater than equals to your maximum value. What is your maximum value? Log 1 by epsilon log 1 by k. Therefore fnx minus fx is less than epsilon for all n greater than n and 0 to x1. So this implies that there exists an n and this condition is satisfied. Hence does for any epsilon greater than 0 there exists n such that for all x belongs to 0 comma k, where k is less than 1, fnx minus fx is less than epsilon for all n greater than equals to n. Therefore the sequence fn is uniformly convergent in 0 comma k, where k is less than 1. So what we did in this question is we take the use of definition. First we show that pointwise convergent, fine, this is a pointwise convergent, and then we show that fn is less than, by definition fn is the fnx of minus fx is less than epsilon. Putting the value of fnx and fx here, taking log both sides and solve that and find the n which is greater than log 1 by e upon log 1 by x. As we see that when you increase the value of x, so this value is going to be increased with x, so its maximum value being at k, x equals to k, so this is your maximum value. Taking n which is greater than is your from your maximum value, so that this condition holds. When this condition holds, then this is uniformly convergent in 0 comma k. Fine. Now moving to the next question. But we just forgot one thing, that they asked us, what they asked us, they asked that is uniformly convergent on 0 comma k where k is less than 1. We just showed that k is less than 1, but we don't prove that why k can't be equals to 1. Why k can't be equals to 1? So if you take k equals to 1, then what is your maximum value? Your maximum value is log this implies log 1 by epsilon upon log 1 by k. If you take k equals to 1, this implies log 1 by epsilon upon log 1 by 1. So this is your log 1 by epsilon by 0, this is your infinity. So k can't be equals to 1. Hence fn x converges to fx uniformly on 0 comma k where k is greater than 1. Fine. Now moving on to the next question. Question number 3. What they ask, show that the sequence fn where fn x equals to 1 by x plus n is uniformly convergent in any interval 0 comma b where b is greater than 0. Now in third question we have to show that the sequence fn where fn x is your 1 upon x plus n is uniformly convergent in any interval 0 comma b where b is greater than 0. Fine. We have to show that this is uniformly convergent. So first we have to prove this is pointwise convergent. Solution: fx equals to limit n tends to infinity fn of x is equals to limit n tends to infinity 1 upon x plus n, and when your n tends to infinity, this whole term goes to 0, so this is 0 equals to 0. Hence by definition of pointwise convergence, we get fx equals to limit n tends to infinity of fn x for all x belongs to 0 comma b. This implies fn x converges to fx pointwise. Fine. Now we are going to show that this is uniformly converging in any interval 0 comma b where b is greater than 0. Uniform convergence. So for any epsilon greater than 0, fn x fx is equals to 1 by x plus n minus 0 is less than epsilon. If n is greater than 1 by epsilon minus x, which decreases with x, so the maximum value being 1 by epsilon. Where this is come from? If you solve this, how? 1 by x plus n is less than epsilon. This implies 1 by epsilon is less than x plus n. This implies n is greater than 1 by epsilon minus x. So the maximum value being 1 by epsilon when x is equals to 0, because the function is this term is decreasing with x. So when x equals to 0, this point will be your maximum. Hence, let n be greater than your maximum value, so that for every epsilon greater than 0 there exists n such that fnx minus fx is less than epsilon for all n greater than equals to n. Hence the sequence is uniformly convergent in any interval (0, b), where b is greater than 0. Fine. In this question, what we have discussed, that first we have find your pointwise convergence, which is equals to 0. So fn is converges to f pointwise. Now we find by the definition of uniform convergence for any epsilon greater than 0, we have to prove that there exists an integer n which is greater from your maximum value. Fine. So fnx minus fx is your this point, and your n is 1 by epsilon minus f, which decreases with the with increase of x. So initial value at x equals to 0, this point is be your maximum. So for that there exists an n greater than equals to 1 by epsilon. So for every epsilon greater than 0 there exists an n such that this condition holds. Hence the sequence is uniformly convergent in any interval 0, b. Fine. So moving to the next question, question number 4. Show that the sequence fn where fnx equals to tan inverse of nx, where x is your greater than equals to 0, is uniformly convergent in any interval a comma b, where a is greater than 0, but is only pointwise convergent in 0, b. This is your a. So we have to show that this fnx, which is equals to tan inverse nx for all x equals to greater than 0, is uniformly convergent in a comma b, where a is greater than 0, but pointwise convergent in 0, b. So solution. So we have to find first your pointwise convergent. Fine. So say same, fx equals to limit n tends to infinity fn of x is equals to pi by 2 when x is greater than 1, because when n tends to infinity, this fnx equals to tan inverse of nx. This implies tan inverse infinity. So this is always be your pi by 2 for x greater than 1. and when your x is equals to 0, this implies tan inverse of 0, which is your 0 only. So this is your 0. Hence fx is well defined and exists for all x belongs to a comma b, a comma b. Hence this is fnx is pointwise convergent. In the last we can show that a is your equals to 0 only. So if you take a equals to 0 initially, x equals to 0, and for x is greater than 1, then this is equals to can be 0. So next we can check uniformly convergence. Fine. Again same, let epsilon greater than 0 be given, so that for x greater than 0, same condition, fnx minus f of x is equals to tan inverse nx minus pi by 2 for less than epsilon, where pi by 2 is your fx here and tan inverse x is given in your question. So this is your, as we know, since cot inverse x plus tan inverse x is your pi by 2, so we can change this term can be cot inverse of nx is less than epsilon. If you put nx here and take cot to those side, and n is less than cot epsilon by x, which again we can find the maximum value of this function, which decreases when x increases. So what is the initial value of x here? Here initial value of x as x belongs to a comma b. So when your x increases from a to b, then this value is decreases. So at x equals to a, this value is your maximum. Hence the maximum value is cot epsilon by a. Fine. In a comma b, where a is greater than 0. So we now choose let n is your greater than from that maximum value cot epsilon by a. Thus for epsilon greater than 0, there exists n such that for all x belongs to a comma b, a greater than 0, this condition holds, less than epsilon for all n greater than n. Fine. Hence the sequence converges uniformly on a comma b, where a is greater than 0. So then what is your problem when a is equals to 0? If you take let a equals to 0, fine, then your cot epsilon by a is become cot epsilon by 0, which is your infinity, so that no such integer n exists such that this condition holds for all n greater than small n greater than equals to 1, and hence Fn is not uniformly convergent on 0 comma b. Fine, and it is only pointwise convergent in 0 comma b. So these are some questions, important questions. You must remember this method, this type of questions, and you can solve in your exams, so you can get your full marks. Fine. So for today this is all yours, and you can enjoy this from my playlist, and my next lecture is going to be topic on test for uniform convergence. Fine. For today, thank you. Bye bye.